All right, AP scholars, we are going to look at the wonderful world of antidifferentiation, which, as the name implies, is the process of undifferentiating. So you've learned how to take a lot of different derivatives, and now we're going to undo that, and it will make more sense why you're doing that in the very near future. But for now, I just want to talk about some quick facts and some skills that you are going to need to use. So first of all, if we look at this simple function, f of x is x squared, if I ask you to take the antiderivative, you've had some practice with this already, but what I'm asking you to do is come up with the function that is the function that, such that if I differentiated it, I would get x squared. So knowing that when you take the derivative of a power function, you lower your exponent by 1, we're going to do the opposite thing. We're going to raise our exponent by 1 to give us x to the power of 3. And then this coefficient is what we need to tackle next. And you probably already see it, but for the sake of more complex problems that you'll see later, let's do it this way. What I want to know is that if I take the derivative of this, I'm going to get 1x squared. So really the question is 3 multiplied by what will equal my coefficient of 1. So I have a simple algebraic equation that I can solve for my question mark to get 1/3. So here it is, and I'll show you this now. We're going to start using this notation frequently. The antiderivative of f of x is capital F of x. This is standard procedure, so let's write that down. So the antiderivative of f of x is f of x, capital F of x, which means, by the way, as a side note, that the derivative of capital F of x, which essentially means the derivative of the antiderivative, is equal to the original function. In normal people language, what this is saying is that if I take the derivative of an antiderivative, I'm going to be back at the original spot that I started. It's a lot like saying if you give somebody $5 and then take $5 away, they have exactly what they started with, right? So that's kind of cool. These are like inverse operations, and that's going to matter a lot when we talk about something called the fundamental theorem of calculus. That is kind of the crux of the fundamental theorem. But I digress. So just one more time, just to make sure that we've got this. If we start with f of x and we differentiate, we get f prime of x. If we go the other direction from f of x, if we anti-differentiate, we get capital F of x. So just as we toss this symbol around all the time, we're going to start tossing this symbol around all the time as well. So let's go back to this example because we're not actually quite done with it. There's one point that is unique to antiderivatives that is worth talking about, and that is that antiderivatives are not unique. Which simply means that there are multiple possible correct answers for any antiderivative. If we look at this example that we've begun with, if f of x is 1x squared and I antidifferentiate to 1/3 x cubed, there is no reason why my answer can't be 1/3 x cubed plus 4. And to prove that to you, let's check this. Let's take the derivative of the antiderivative. If I differentiate this function using my power rule, I'm going to take 3 times 1/3, and I'm going to end up with 1x to the power of 2 plus the derivative of 4. And the derivative of 4 is equal to 0, which is correct because that was my original function f of x. Now, the same could be true if I had said that the antiderivative, f of x, capital F of x, is 1/3 x cubed plus 2, right? Because the the derivative of 2 is also 0. And in fact, this constant could have been 21, or it could have been 217, or it could have been 2,174. It could have been any constant, because the derivative of any constant is always 0. So there's a way that we accommodate that when we take an antiderivative, and that is to, instead of coming up with a number or making up a number or saying that this could just be some random number, we call it something, and that thing that we call it is c. So whenever you take an antiderivative, you're going to make sure that you add a constant which is representing c, because when you take the derivative of any constant, whether it's negative pi or e or 10.6 repeating, its derivative is 0. So back to our definition, the antiderivative of f of x is capital F of x. Let's modify this and incorporate that new tidbit of information, which is plus c, where c represents any constant. And now we will soon answer questions where we are able to actually evaluate what c specifically is. We might have an initial condition, so we might say that on the original function, when the input value is 2, the output value is 10, or something like that, and that would allow us to be able to actually solve for c. But in general, if I'm just finding a general antiderivative, I'm always going to remember to add c because I have to accommodate the fact that there could be some constant added on the end because its derivative is 0. Alright, so let's look at some example here. We've got f of x is equal to 2x to the power 4 plus 18x squared, and what I'm interested in finding is the antiderivative, capital F of x. I have a power function, a polynomial power function, so I'm going to undo my power rule. So the very first thing that I'm always going to do is deal with the exponent. It was a 4. I know that to take the derivative I have to go down 1, so if I'm anti-differentiating, I'm going to go up 1 to 5. And in the same way over here, I'm going to make this 2 into a 3. And now I deal with these coefficients, and let's start with this guy because this is a little bit easier. What I need to ask myself here is, and you'll start doing these in your brain, I'm just showing you the thought process involved here. 3 times some constant coefficient will equal 18. This is me unpacking the power rule. I'm going backwards. So I'm saying 3 times what is 18, and obviously that thing is 6. So my coefficient is 6. This one's a little trickier because I'm going to end up with a strange decimal. Not so strange. I know that 5 multiplied by some constant coefficient is equal to 2, and when I solve this thing, I end up with 2/5. So let's make this guy into 2/5. And I'm forgetting one thing before I'm done. I've got to remember that I've got to add my constant, which accommodates the fact that the antiderivative of nothing is some constant number. So there we go. And if I feel weird about this, even if I don't feel weird, I should just check it. I should always check this and make sure that I'm on the right track here. Let's take the derivative of this, and if I take the derivative, I should end up with the function that I just anti-differentiated. So let's do that. I'm going to take 5 multiplied by 2/5, and I'm going to end up with the 5's canceling out. So I'll have 2x to the power of 4 plus 18x squared plus 0, because the derivative of my constant c is 0. And I see that that's what I started with, so I am good to go. Alright, one more for good measure here. I am interested in finding the antiderivative of f of x. So if we toss some trig into the mix, I've got to ask myself, the derivative of what is equal to sine? And I'm tempted to say cosine, but I should stop and pause and remind myself that if f of x is equal to cosine, the derivative of cosine is equal to, not sine, but negative sine. So I've got to deal with that negative somehow, and the way that I'll deal with that is by putting a negative out in front. If I take the derivative of negative cosine of x, I end up with a negative sine of x, which is positive sine of x, which is what I am trying to get back to, so we're good to go. I have an exponent here of 1, so I'm going to raise that power by 1 to get to 2, and now I ask myself, in the process of anti-differentiating, 2 times what would give me 4, and the answer is 2. Plus my constant c, and I'm good to go.